Hello friends, we have been initiating our discussion in previous few lectures with an elegant way of representing the mechanical behavior of a specific category of materials called metals and alloys. So we start with this rather straightforward description of the mechanical behavior that is offered by metals and alloys, and we have built on that specific way of representation. However, in the previous lecture, what we attempted to do was we attempted to consider what are the different assumptions that get into this specific representation of the mechanical behavior of metals and alloys, and we saw is there any way for us to relax these assumptions. So this representation involves two critical components to describe any mechanical behavior or any behavior of any materials. So it involves the mechanical condition that we impose along the y-axis and the response offered by the material along the x-axis. So this response can be elongation or it can be strain, and along the y-axis we have this mechanical condition that we impose. It can be load or it can be stress. Now the reason we have rather largely focused on metals and alloys is primarily because their response can be represented by a curve. So despite their differences in the chemical composition, the chemical makeup, when we are talking about metals and alloys, their response can be represented by schematically using this curve. And that's the reason we have largely been focusing on the specific category of materials. Now, when we express or when we describe or graphically illustrate the mechanical behavior of metals and alloy using the sketch here, what we inherently assume is we consider a sample and there is a uniaxial stress that is imposed to it. So we implicitly assume that a uniaxial tensile load or a uniaxial tensile stress is imposed to it. So correspondingly, in response to this uniaxial tensile loading, there is a deformation, or rather there is a change in the dimension of this sample. So there is a longitudinal change in the dimension of the sample, longitudinal change in dimension, and that is exclusively taken care, or that is exclusively rather considered in the x-axis, and this form of loading is considered in the y-axis. Now in the previous lecture we saw that when we impose a uniaxial tensile loading, the longitudinal change is not the only change that is offered by the material. So when we talk about the response, the longitudinal change is not the only change. There is also another change that occurs in a perpendicular direction. So when we consider the uniaxial loading, particularly in this direction, there is the loading direction which is parallel to that of the longitudinal direction. So we have a longitudinal direction and the loading direction is parallel to the longitudinal direction. So that is the reason why we see an expansion along this direction. However, this loading direction is perpendicular to the lateral direction or the lateral side. So if we assume this as the longitudinal axis, there is also a lateral axis and the loading direction is perpendicular to this lateral axis, the lateral direction or the lateral axis. In response to this uniaxial tensile loading, there is also a dimensional change in the perpendicular axis. There is also a dimensional change in the lateral axis. And this dimensional change is quite opposite to that of the dimensional change that we observe in the longitudinal axis, that is in or along the lateral direction or along the lateral axis. There is a decrease in the dimension. For a uniaxial loading of this form, even though there is an increase in the dimension along the longitudinal axis, there is a decrease in the dimension along the lateral axis. Now we saw in our previous lecture that there is a parameter that can be used to describe both these change in the dimensions. So we have a change in the dimension along the loading direction and also a change in the dimension perpendicular to the loading direction, and both these can be expressed by using a parameter called Poisson's ratio. And this effect that we see is called as Poisson's effect, and the ratio that includes what we mean by Poisson's effect is the change in the lateral dimension when principally a load is applied along the longitudinal axis. So a load is applied along the longitudinal axis, there is an expansion that corresponds to it, and in addition to it, in relation to the longitudinal expansion, you also see there is a decrease in the dimension along the lateral plane or the lateral axis. This we refer to as the Poisson's effect, and the ratio that includes both the change in the lateral dimension and also the longitudinal dimension is called as Poisson's ratio. So if the strain in the lateral dimension is represented by epsilon lat and the strain in the longitudinal dimension is expressed by this term here, then this ratio along with a negative sign is called as Poisson's ratio. Now the negative sign is here primarily because the change in the dimension that we observe in the lateral direction can be assumed to be achieved by, or can be viewed to be achieved by, a resultant compressive load, and when we have a compressive load that is acting, by convention we need to include this negative sign, and therefore the Poisson's ratio comes up with a negative sign because the dimensional change that occurs in the lateral direction is similar to the ones that you observe when you impose a compressive loading. Now by including the change in the dimension, or by including the response offered by the material in the lateral direction along with the longitudinal direction, we have relaxed the first assumption that this schematic representation considers. So there are two assumptions that schematic representation considers. One is it assumes there is a uniaxial tensile loading. Secondly, what we observe is it exclusively considers change in the longitudinal dimension. Now when our schematic representation stems from those two assumptions, now by considering the lateral change in the dimensions, we have now relaxed this one assumption. Now by considering this Poisson's ratio, by using this Poisson's ratio, we will now be able to describe both lateral change in the dimension or the lateral strain and also the longitudinal strain, and for a given material, particularly when we are considering the ratios between the strains. So the strains, the reason for introducing or talking about the response or expressing response of a material in terms of strain is because all the dimensional influence, the influence of the dimension on the response of the material is removed. So whatever we see when we discuss in terms of strain is exclusively the behavior of the material. Now that we are taking or normalizing the behavior of the material, the lateral behavior with respect to the longitudinal behavior, we are exclusively discussing or describing the property of a material. So Poisson's ratio, it talks about exclusively about the property of the material by considering both the lateral change in the dimension and the longitudinal change in the dimension. So when we involved Poisson's ratio, the response that we are talking about is not exclusively associated with the change in the lateral dimension alone, it is also associated with the longitudinal dimension. It combines both longitudinal and lateral dimension. It combines both the deformation, the expected deformation along or expected change in the dimension along the loading direction and also in the direction that is perpendicular to it. Now, the other assumption that we have associated with this particular representation of the load elongation or stress strain curve is the uniaxial loading. So far we have been largely considering the uniaxial tensile loading. Now in the previous lecture, we considered or we looked into what would be the change or what would be the difference in the response, or how different would be the response offered by the material when we have, instead of uniaxial tensile loading, a bi-axial tensile loading. So as the name indicates, in case of uniaxial tensile loading, we have the loading direction that is primarily along, that is exclusively along one axis, that is the longitudinal axis. Now in case of biaxial tensile loading, we have the loading direction along the two axes. One is, of course, we start with the longitudinal axis, so loading is along this direction, and in addition to this direction of loading, there is also along the one of the lateral directions. So in case of a three-dimensional system, we have numerous lateral directions are possible. In that, along one of the lateral directions, we have another tensile loading that is acting. So we have now moved away from another assumption, that is, in the initial case, when we considered, when we came up with the schematic representation, that is here, when we consider this case, when the schematic representation was initially introduced, we have uniaxial tensile loading. Now we are moving away from that assumption and we are considering biaxial tensile loading. Now the response offered by the biaxial tensile loading can be categorized into two. This is something that we saw in our previous lecture. So if we express this longitudinal loading condition, so if we consider a coordinate system as x and y, the stress along the x-axis can be represented by this and the stress along the y-axis can be represented by this. Now the response offered by a three-dimensional material, a sample material, to a loading condition that involves both. So we are imposing simultaneously sigma x and sigma y. So biaxial loading condition involves these two stresses that are simultaneously imposed on the material. Now in this case we have two responses that are offered by the material. So one is referred to as the one, we can, for our discussion sake, we can call it as a direct response, and other we can call it as an indirect response. So there are two kinds of responses, two types of responses that are offered by the material. Now the direct response is along, so one way of characterizing the direct response is it is along the loading direction. So the direct response is along the loading direction. Now when we are applying longitudinal stress along the when we are applying sigma x stress along the longitudinal direction, the direct response is along the same direction. When we are applying sigma y stress along the lateral direction, the response is also along the same direction. So if we consider the response, the direct response in green, so the direct response for sigma x will be in this direction and the direct response for sigma y will be in this direction. Now if we consider the indirect response offered by the material, then the indirect response for the sigma x, so the indirect response for the sigma x will be in the perpendicular direction. So the indirect response for sigma x will be in this direction, whereas in the same way the indirect response for sigma y will be in this direction. So the direct response will be along the loading direction, whereas the indirect response will be perpendicular to the loading direction. Because of these differences in response, we need a way to describe these responses. So we have direct responses, we have indirect responses. So in order to make these distinctions, we need to have a unique way of describing these responses, and therefore even though we use the same term epsilon, the number of subscripts that we use will actually increases. So essentially in this case, since we have now a bit more complex loading condition, the response now is of two types. So earlier in the uniaxial case, we have a change in the lateral direction and the longitudinal direction. So we were able to distinguish these two as lateral and longitudinal strains. However, in this case, now in the present case, we have biaxial tensile loading, and correspondingly the strains associated with it also increases. The complexity of the strain associated with it also increases. So then we need an appropriate terms, appropriate parameters to describe, to distinguish one form of the strain from another. So therefore we include a term that comprises of two subscripts. So when we have two subscripts, we need to describe what each of these subscripts mean. So the first term, the first subscript, it indicates the strain direction, the direction along which we observe the response. So the strain direction is nothing but the direction along which, so this is the response direction. The strain or the response direction is the direction in which we observe the response, and the second term is the loading direction. So because of the complexity associated with the loading condition, we need appropriate parameter to describe the strain. So therefore we have strains with two subscripts. The first subscript, it describes the direction of the response. The second subscript, it describes the loading direction. Now let us begin with sigma x. So sigma x is the load that is acting along the x-axis. So there will be a strain along the x-axis. So in response to the load along the x-axis, there will be a strain along the x-axis. So therefore, since the strain is along the x-axis, the first subscript will be x, and since the load that we are imposing is also along the x-axis, the second subscript will also be x. So this term indicates the strain along the loading direction for the x-axis. When the loading direction is x-axis and the strain is also along the same direction, then we describe the strain in this manner. Now, in response to this sigma x, the loading along the x-axis, there is also a strain along the y-axis due to Poisson's effect. Now, the Poisson's effect comes into play, and this, because of this Poisson's effect, there is a strain that is associated along the y-axis. So y-axis is the response direction that comes first, and this happens because of the stress along the x-axis. So for one given direction of stress, there are two different strains appear. One is the strain along the loading direction, and the other is the strain perpendicular to the loading direction. So in this case, this is the direct strain, and in this case it is the indirect strain. So what we observe here is, as the complexity of the loading condition increases, so does the way we describe the strain also increases. The complexity associated with the response also increases. Now in case of uniaxial tensile loading, it was rather straightforward for us to talk about longitudinal strain and lateral strain. But here, since we are having a bit more complex loading condition, we have to increase the number of subscripts, or we have to introduce a way to describe the response associated with the material, and therefore we have a parameter, a term with two subscripts associated with it, and ultimately we end up having this representation. So as the complexity of the loading condition increases, so does the way we describe the strain, the response also increases. So does this response offered by the material increases. So as the loading condition becomes complex, so does the response offered by the material. Now when we extend the same understanding to the stress that is imposed along the y direction, now the direct response for the stress offered along the y direction will also be in the y direction. So it will be epsilon y, and the loading direction is also y. In case of the indirect response, what we end up having is the response is along the strain is along the x direction, but the loading is still along the y direction. Now essentially, so this would be the direct response and this would be an indirect response. So these two parameters, the epsilon with identical subscripts, they indicate direct responses or direct strain, with dissimilar parameters or dissimilar subscripts, they indicate indirect responses. Now the question is there a unified way of describing what is the stress along a specific direction? So we have introduced a coordinate system of x and y axis, and we have our sample, and there is load that is being applied in both y and also in the x-axis. Now the question is it possible for us to express what is the strain, the total strain along the x-axis and the total strain along the y-axis? Now the question is it possible for us to arrive at an expression that describes this total strain along the x-axis and the total strain along the y-axis? Now since we want to express the total strain along the x-axis, so this term here represents total strain along x-axis. Now this expression can be described, or this particular total strain, or this term can be expressed as the sum of the two strains that we observe along the x-axis. So if you could recollect, the first subscript, it indicates the direction of the response. The second subscript, it indicates the load direction. So when you consider these four terms, there are two terms that offer response along the x-axis. So that is this term and this term here. So these two terms, since the x comes in the response direction, so the sum of all the response along the x direction gives us the total strain along the x-axis. So therefore the total strain along the x-axis is epsilon xx plus epsilon xy. So this is the total strain along the x-axis because we have identical direction, so identical response direction. Now let us try to relate, or let us try to have an expression that involves also the stresses, the two stresses, that is sigma x and sigma y, that brings about these four responses. So we now have an expression for the total strain along the x direction. Now let us have a generalized expression that helps us get rid of these complex notation, and let us attempt to have a simplistic or rather straightforward or approachable expression, because this expression, it involves these complex two subscript terms. So let us try to see if it is possible for us to get rid of it. Now when you consider the load along the stress along the x-axis, this stress is perpendicular, or is in the sense we are confining ourselves to the elastic deformation. Our focus is largely on the elastic deformation or elastic change. This stress is directly proportional to the strain that we observe in that direction. Let me repeat, we are imposing a stress along a specific direction, in this case x direction, and we are imposing a stress that is within the elastic range, and within the range this stress is directly proportional to the response that we observe in that direction. So the response that we observe in that direction is this term here, so there is a proportionality that is associated with it. Now the constant of proportionality, this sign can be replaced with equal sign, and the constant of proportionality is the Young's modulus along that direction. So Young's modulus along that direction will help us arrive at this expression where we are able to relate the stress that we impose along the x-axis to the strain that we observe, the response that we observe for the stress along the same direction, and that is possible because we have considered the Young's modulus along that direction. Now in the same way, it is also possible for us to arrive at an expression for the direct response along the y direction. In the same way, it is also possible for us to arrive at an expression for a direct expression for the strain that we observe, to arrive at an expression for the direct strain that we observe along the y axis. So we have a stress along the y axis, there is a response along the same axis that is given by epsilon yy, and the constant of proportionality is Young's modulus along y axis. Now it is possible for us to assume that irrespective of the direction, the constant, that is Young's modulus, is the same. So along the x and along the y, the Young's modulus is the same. It is E. So we are assuming that the material that we are considering as the same constant value, it assumes the same constant value along the x-axis and along the y-axis. So such materials are called as isotropic materials. So very rarely we observe such phenomena in metals and alloys, but for our discussion, let us assume that the Young's modulus of the material, it is independent of the direction. Along the x-axis, it is the same Young's modulus. Along the y-axis, it is the same Young's modulus. So what it essentially means is that now when you are loading your sample along the x, or when you are loading along sample along the y, that is within the elastic range. Again, we need to remember that. So when it is within the elastic range, then the constant of proportionality that relates the stress to strain is same in both x and also in the y direction. So when you are in the elastic range and you are imposing a bi-axial tensile loading, then the response you get along the x and y axis, the constant proportionality that controls this response is same in both directions, and that is true for a special category of materials called isotropic materials. So in that case, we can get rid of the subscripts for the constants. So what we end up having is ultimately sigma x is equal to E epsilon xx and sigma y, which is equal to E epsilon yy. So this expression we are able to arrive at for a special category of materials called isotropic material. Now what we have arrived then is an expression for sigma xx. Now sigma xx can then be written as, or rather epsilon xx, pardon me, the response epsilon xx can be written as the ratio of sigma x by E. So we can substitute this particular expression for sigma xx here, and when we do that, we end up having the overall strain along the x-axis is the ratio of the load along the x-axis and the Young's modulus plus the indirect response that we observe along the x-axis. So we were able to replace the first complex term with the stress that we impose along the x-axis and a material constant. Now we need to replace the term that is associated with the indirect stress. Now this so this indirect strain that comes from the stress along the y-axis. So this term here, this response here, it is along the x-axis, but it is because of the stress along the y-axis. So the strain, this response, even though it is along the x-axis, the stress that brings about the strain is along the y-axis. So in that case, one way of relating the stress and the indirect response. So the reason why we have the stress along the x-axis despite the load being imposed along the y-axis is because of the Poisson's effect. The reason we have such an indirect strain is because of the Poisson's effect. So correspondingly, we can use the Poisson's ratio to describe the indirect stress. To describe this indirect stress, rather the indirect response, we can make use of the Poisson's ratio. So the Poisson's ratio for the load along y-axis is, so we are considering the load along the y-axis, we are considering the stress along the y-axis because that is what this particular term corresponds to. So the Poisson's ratio for the stress along the y-axis will consider the negative of the, so this here will consider, so this is for the load along the y-axis, this considers the negative of the strain along the x-axis to the strain along the y-axis. So what we essentially have done is, the second term, it involves a response offered by the material along the x-axis for the stress that is imposed along the y-axis. That understanding we gain from considering these two subscripts here. Now, the only reason why we have a strain along the x-axis for a load along the y-axis, a strain along the x-axis, a strain along the x-axis for a load along the y-axis is primarily because you are imposing a load along the y-axis and we observe a strain along the x-axis is primarily because of the Poisson's effect. So therefore, we consider what is the Poisson's, the corresponding Poisson's ratio that brings about this strain here. So therefore, we are considering the corresponding Poisson's ratio for the load along the y-axis. And when we do that, the Poisson's ratio is nothing but the ratio of the lateral strain to that of the longitudinal, or the ratio of the strain along the perpendicular direction to that of the loading direction. So we are considering the Poisson's ratio because of the load direction y. So therefore, in the numerator, we need to consider the strain along the perpendicular direction, that is x. So therefore, we have the corresponding strain in the numerator. In the denominator, we need to consider the strain along the loading direction. So therefore, the corresponding parameter is mentioned here. So once we are able to arrive at this expression, now we have already arrived at an expression for epsilon yy. So this is the expression that we have arrived at for epsilon yy. So we have epsilon yy that is related to the stress that we have imposed and the constant here. So therefore, we can express the epsilon yy, which is here. So epsilon yy is nothing but sigma y by E. So we can substitute that here. So therefore, when you substitute the epsilon yy here and then bring this here, then epsilon xy. So you need to substitute, so epsilon yy, we need to substitute these two, and then we have to bring this term here. So when we do both these operations, then what we end up having is this term here, the indirect strain epsilon xy, is nothing but minus of the product of epsilon yy and the Poisson's ratio along the y direction, which can be expressed as minus sigma y, the Poisson's ratio along the y direction, and E. So the strain, the indirect strain along the x direction can be expressed in this manner. So what we have is, we have in this expression, we have the stress that brings about the strain, that is sigma y, the Poisson's ratio along the direction, the same direction, and the Young's modulus. Now since we have considered an isotropic material similar to the Young's modulus, the Poisson's ratio along the y direction is equal to the Poisson's ratio along the x direction. So the Poisson's ratio is independent of the direction, because we have assumed that it is an isotropic material. The Poisson's ratio is independent of the direction. So ultimately this expression simplifies as the ratio between two constants, that is Poisson's ratio and Young's modulus, along with the loading direction that brings about the strain epsilon xy. So we have epsilon xy, an expression for epsilon xy, and we also have an expression for epsilon xx. So epsilon xx is written as sigma x by E. So this we have arrived at here. So epsilon xx is the ratio of sigma x by E, and we have arrived at an expression for epsilon xy. Now we can combine these two, because the overall strain along the x direction is the summation of the direct strain along the x direction plus the indirect strain along the x direction. So when we sum these two up, what we end up having is sigma x by E minus Poisson's ratio, Young's modulus, and y, and it is possible for us to bring this 1 by E out, and what we end up having is sigma x minus Poisson's ratio. So this is the ultimate expression. So the overall strain along x-axis under bi-axial tensile loading is of the form that we have right now derived, that is epsilon x, the overall strain is 1 by Young's modulus sigma x minus the Poisson's ratio and sigma y. Now we can do the same steps. We can take the same steps for the y-axis, for the overall strain along the y-axis. When we take the same steps for the overall strain along the y-axis, it would be the summation of the direct strain along the y-axis, that is epsilon y plus the indirect strain along the y-axis, that is epsilon yx. And ultimately you will end up with an expression of the similar form here, that is 1 by E sigma y, because we are talking about the overall strain in the y direction. So this expression is the overall strain in the y direction. So it will be sigma y epsilon sigma, or rather the Poisson's ratio sigma x. So ultimately the strain along the x-axis will be of the form 1 by E sigma x minus Poisson's ratio sigma y, and along the x-axis, the overall strain along the x-axis is 1 by E. So these are the strains that we observe along x and y axis for a biaxial loading condition. Now when you consider a uniaxial tensile loading along the x-axis, so uniaxial tensile loading along the x-axis, in this case what we observed was the strain that we observed along the x-axis was just the longitudinal strain, and the strain that we observed in the y-axis was just the lateral strain. So these are the two strains that we observed for a uniaxial tensile loading. However, when we have a biaxial loading condition, the strain adapts a complex form such as this. So this is the case for the biaxial tensile loading. For x-axis we have a complex expression like this, and for the y-axis an identical but similar relatively complex expression. Or however, in case of uniaxial we have a simplistic representation of the strain along the x and y axis. We have a single term representing the strain along the x and y axis, whereas in case of biaxial tensile loading the corresponding responses are a bit expanded, and we need to include the Poisson's effect to describe it. So what we have essentially observed is when we consider or when we increase the complexity of the loading condition, then correspondingly the strain that we observe, the response that we observe increases, and the way we describe it also increases. And if you could notice, even the just representation of it would require too many subscripts. So depending on the loading condition, we need to have sufficient amount of information to describe the response offered by the material. So with this, since this brings to an end some of the specific consideration that we have offered to the stress strain curve, we will wind this lecture up now, and in the subsequent lecture we will get into some new topics on how the material behaves when we consider rather the entirety of the sample, not just a specific direction but the entirety of the sample. That is what we will be looking into in the subsequent lecture. Goodbye.